force is any push or pull. So any push or pull. It can be a push from a physical push that you or I might push on something or pull on something, or it could come from gravity. But any push or pull gives us a force. There are 4 different ways that we might see forces in this class. One of them is if they're both pushing in the exact same direction. Anytime they're in the same direction, you're going to add them up. So I would say 20 newtons plus 30 newtons equals 50 newtons, and I would say that that's going to the right. Another way that might happen is that they are going against each other. So I have 20 newtons to the right plus 30 newtons pushing back to the left. Sorry, here you would subtract them. Anytime they're going opposite each other, they would subtract. So 20 newtons minus 30 newtons equals negative 10 newtons. Now, the biggest thing about the negative is just that it's saying that it's going in that direction. So you conceptually have to look at it and figure out, well, which direction is it going? So I would say that I've got 10 newtons to the left is what's happening here. The third way that this happens is where they are directly at a right angle to each other. And so if I were to be pushing up and over, the object would be moving somewhere along this line. Every time it went up a little bit, it'd go over a little bit, up a little bit, over a little bit. And you wouldn't see each of those. You would see a straight line. The way that we draw that out is we actually make a rectangle out of this. Just like that. And the line that you end up traveling on, think about it like you pull back a slingshot. If I pulled back a slingshot like this, it would shoot over to the next corner. And so you would draw that in here. Start there, have it go to the other corner, and you'd make sure that you put an arrow on here to show which direction it's going. Now, with a rectangle, you know the force going up, you know the force going over. Right now they're drawn like this, but I could put this over here instead, and then I have A and B, and if I'm looking for C, I can use the Pythagorean theorem. So I could say 20 squared plus 30 squared equals C squared. And so when I do that, I end up getting 1,300. 20 squared plus 30 squared equals 1,300 equals C squared. And when I need to get rid of the squared, so I take a square root of both of them, and I end up with 36.0 something something something. So I'm going to leave it at 36 equals C. What that means is that the net force on whatever's being pushed that way is 36 newtons. Now the last way that we have is dealing with something that is at an angle that's not a 90-degree angle. And you can break it up mathematically and figure out exactly what you have, but what we're going to do is we're going to measure it. And so my line here is 20 centimeters. My line here, sorry, is not 20 centimeters. It's 2 centimeters, 10 centimeters, 10 newtons per centimeter. 3 centimeters here, so 10 newtons per centimeter. And I'm going to, so I'll write that here. 10 newtons equals 1 centimeter. And in order to calculate that, I actually need to take and draw the parallelogram. It's called completing the parallelogram. So I'm going to take and draw my line into here. I'm going to draw this one coming out here that ends up being that same length. And I'm going to draw this one coming up here that ends up being that same length. And they should be parallel to each other. So this is parallel to that. This is parallel to that. And what happens, again, think about a slingshot. If I put something in here and pull it back and I let it go, it's going to shoot across this way. And so that's the line that I would draw in. Ends up going across like that. Now, if you're careful about what you're doing and you keep things to scale, as we talked about, the measurement here is as good as your calculation. So if I take and I measure this here, I'm right at 4.6 centimeters right here. And so if I said 4.6 centimeters, and then I know that I have 10 newtons in each centimeter, so I would say 46 newtons. And if you're not in one of these three situations where you can use the math for it, then you can use the drawing, draw with precision, and you'll be able to get that calculation. Another part of what we talked about when we were talking about doing forces is the equation that we use. It's force equals mass times acceleration. Force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. We see this as F equals ma, and we need to keep in mind that 1 newton is equal to 1 kilogram time meter per second squared, and our units here represent that. So if we're dealing with a problem that is using this equation, we would have something, there's two different problems that we'll walk through here. One of them is a cart is pushed with a force of 75 newtons, and it has a mass of 12.5 kilograms. How fast is it accelerating? So I'm looking for the acceleration here. Well, F equals ma, so I'll write that in here. And in this situation, I want to solve for a, which means I need to bring the m over to the other side. Currently, m and a are being multiplied, so the opposite of that is to divide it. So I have the equation that a equals f over m. I can take my variables and put them in. My force is 7.5 newtons, and my mass, 75, sorry, that was right, 75 newtons. My mass is 12.5 kilograms. And I know that newtons break up into kilograms times meters per second. So I have 75 kilograms times meters per second divided by 12.5 kilograms. So the kilogram unit cancels out. And 75 divided by 12.5 gives me, if I take 75 divided by 12.5, I get 6, and I'm left with meters per second equals, meters per second squared on all these, sorry. Meters per second squared is what's my acceleration is going to be equal to here. So I have F equals ma. I bring the m over. So I have A equals force divided by mass. I have the force of 75 newtons divided by the mass of 12 kilograms. We know that newtons break up into kilograms times meters per second squared. So I have 75 of those divided by 12.5 kilograms. The unit of kilogram cancels out, the numbers stay. 75 divided by 12.5 gives me 6 meters per second squared, and that would be my acceleration there. Example 2, it's a little bit different because what we have is a box being pushed with a force of 450 newtons and friction pushing against it. So we have to go back to what we did over here. We have one thing going one direction, one thing going the other. So we'll end up subtracting. We have to do that first to figure it out. And sometimes, depending on the situation, sometimes you'll be adding, sometimes you'll be subtracting, sometimes you'll use the Pythagorean theorem or draw to figure out the net force before you use it in the calculation. So in this situation here, we have our box. It's being pushed with 450 newtons. And against it, we have 200 newtons. And we have to get that first. So they're going against each other. So I'm going to take 450 newtons minus 200 newtons. I'm going to get that I have 250 newtons left. This now becomes my force. So when I write out my variables, I have my force equals 250 newtons. So whatever you have up here, you figure out what your total force is with all of those. That is the F that you use. And then we have that it's accelerating at 4 meters per second squared, and we need to find the mass. Well, again, we start with F equals ma, and this time we want to find the mass. So right now mass is being multiplied by a, so to reverse that I need to divide and cancel out there. I have that, so I have m equals force divided by acceleration. So I've got 250 newtons divided by 4 meters per second squared. And when I divide that out, I get 62.5, and I'm measuring a mass, so it would be kilograms. If I break up newtons, cancel out the meters per second squared, the kilograms are the things that are left. So two types of force equations. The first one is straightforward, where you have one force, you have one mass or acceleration, and you're trying to find the other thing. Or sometimes you'll have mass and acceleration, and you're trying to find the force. But you don't have to worry about summing the forces. The second is where you have multiple forces, and you need to figure out what's happening to get the total. In this case, we subtracted them because they were against each other. And once you have that, that becomes the force, and you calculate from there. And there's various problems in each situation that we work with.